Hey everybody, Darienne here. Suraj, Chloe, and I decided to look into a new kind of imaging modality for our project called optical coherence tomography, or OCT. So what is OCT? Essentially, it's a non-invasive imaging of the eyes, specifically the retina, as you can see in this picture here. It uses electromagnetic radiation, specifically infrared. Waves are reflected and transmitted at boundaries between the different layers of the eye, similarly to ultrasound. OCT technology is important because it allows the observation of individual layers of the retina as well as the optic nerve, and this is very helpful for diagnosis of certain eye disorders such as glaucoma, retinal detachment, macular degeneration, and other eye diseases. The key to OCT is it helps us find these things at an early stage of development to prevent blindness later on.
Here we can see the components of an OCT. The OCT starts off with a superluminescent diode, which creates low coherence light over here. Next, the light beams go through a collimating lens to make them parallel. And next we have a beam splitter that turns the light beam into a probe beam that goes in this direction and a reference beam that goes in the C direction up here. The reference beam bounces off of various mirrors that are at known distances that are used as a baseline. The probe beam then bounces off of a rotating mirror that controls the X and Y direction of the scanning. The probe beam reaches the sample and again is transmitted and reflected at various layers in the sample like we saw in ultrasound. After the probe beam and the reference beam bounce back off of their respective destinations, they go to a beam reducer and finally a photodetector and an interferometer. The photodetector and the interferometer calculate something called the echo time delay. There's always a time delay between when the reference beam reaches the photodetector and the probe beam reaches the photodetector. And this value is calculated to produce a range of time delays. If both the beams reach at the exact same time, it causes positive interference. And therefore, an interferometer is able to integrate several data points over a 2 millimeter depth to construct the final tomogram. And OCT is a very shallow imaging modality because of this.
So now we're going to talk a little bit about how to interpret an OCT scan. An OCT scan looks almost like a color map with warmer colors showing thicker retinal areas and cooler colors showing thinner areas. White is the thickest with high reflectivity and black is the thinnest. All machines have a thickness map displaying average retinal thickness values. Here we can see a normal retinal scan with OCT, with the nerve fiber layer being the red lines and the inner and outer plexiform layers of the eye showing up as green and yellow. Retinal thickness is so important because it can be used to monitor the disease process and treatment response. Artifacts in OCT can mostly be attributed to eye movements. Operator-related artifacts show degraded images due to poor focus. Two artifacts in OCT which can lead to misdiagnosis are red disease and green disease. In red disease, it is common to see red areas in the results of a reliable OCT scan with no disease. This could mislead doctors and lead to unnecessary treatment. In red disease, software interprets actual glycomatosis damage as normal, showing a false negative diagnosis. The artifact we see here is the mirror artifact, which can be triggered by certain conditions such as a lesion or macular traction in the eye. This is caused when the Fourier domain cannot distinguish from positive and negative time delays. Because it is non-invasive and quick, OCT is commonly used in the diagnosis and management of retinal disorders. Macular holes, which occurs when vitreous or fluid in the eye shrinks and pulls away from the retina, is a condition that blurs central vision. The macula is the small, light-sensitive area in the center of the retina. This condition can be caused by aging and stress. A stage 3 hole, which is seen here, is completely hollow. The majority green in the image indicates immediate reflectivity. OCT can detect decreases in retinal thickness and increases in reflectivity of the RPE detachment, which results from the lessened ability of the atrophic retinal tissue to attenuate light. This is seen here in a case of atrophic macular degeneration. This allows for greater penetration of the laser beam to deeper structures like the choroid and greater reflectivity. The reduced retinal thickness and volume can be seen on the image below.
Some of you may have heard of Dr. Adam Wax, a Duke biomedical engineering professor. Dr. Wax is the interim CEO of Lumedica, a company founded in 2014. Lumedica's primary focus is the commercialization of a low-cost OCT device designed by Dr. Wax himself. A quote from their website says it best. OCT has been available for over 25 years but remains an expensive technology to manufacture and operate. A patent-pending, low-cost, lightweight system has been devised that will revolutionize eye disease detection. The Lumedica system is small, powerful, and simple. It can be deployed as a standalone screening instrument integrated with an artificial intelligence data diagnostic or as the front line of an eye care network. We were lucky enough to meet with Dr. Wax to discuss some components of his novel technology, and he was excited to share it with us. How did you become interested in OCT technology? Like, was there a defining moment that kind of piqued your interest in it?
So OCT's been around for a while. I remember in graduate school, this is in the 90s, it was a really exciting technology that was developing, but I'd always resisted working in that area. I've been colleagues with Joe Izat, who's on the other side of this wall, which is why I'm pointing over there. That's his office. And he's been such a leader in the field of OCT that I always sort of stayed out of that area. But it was actually interactions with my colleague, Professor Nimi Ramanuyam, who showed the way for providing accessible technologies. So
How are you able to reduce the form factor and cost of OCT while still maintaining performance and also increasing the adaptability of the product?
One technology my lab has adopted is 3D printing. Really almost a magical technology because you can have an idea, sketch it out in a program like SolidWorks and print it that same day. This has really shortened the design cycle for engineers. In the past, if you wanted to make something, you would have to make mechanical drawings, take it to a machine shop, they would make it, and maybe it would work, maybe it wouldn't, but if it didn't, maybe you'd be drilling extra holes in it or you'd have to send it back. And so it might be weeks before you got the next part back. On the other hand, with 3D printing, you formulate the idea, you make the drawing, you print it, and you can try it out that afternoon. And if you don't like it, the next day you can try a different version. So we've adapted this for OCT imaging. In OCT, the detector is a spectrometer. This is a device where you break up light into all the different wavelength components, and so you have to detect each wavelength. And typically, for years and years, spectrometer were these really high precision devices. But the priority is different in OCT. You have some room for slop. You can have some tolerance there. The key aspect is that it goes fast. So usually in OCT, you're trying to focus a beam onto a very narrow detector. One of the innovations that we use is we use these tall aspect detectors. So we're able to relax the tolerance in the vertical direction. So we can have a slight misfocus in that direction. We can have slight misalignment in that direction. In fact, we had to build this into our spectrometer. The idea that because it was 3D printed, that things might move. They might heat up, they might flex. So in our spectrometer, we take several steps. In addition to the tall pixels, we have a unique patented design called a loop spectrometer. So usually spectrometers have a geometry where light comes in and follows some path. We make ours with a loop configuration that has reciprocating arms, so that if I have something that extends or contracts due to temperature change, then I have a reciprocating action on the other arm. So it can actually heat up and cool down and stay in line. When we were first building these, they were so robust that we would take them out on sales calls, and my partner would freak out because I'd be like, "Look, you can drop it." And I'd pick it up and I'd drop it on the table, and it would stay in line. We would put it in the cargo hold of the plane, and we would take it out. Before we go on the sales call, we'd set it up in the Starbucks, and we were doing OCT in the Starbucks. Unprecedented. I mean, no one had ever thought that your OCT could do this kind of thing. We're starting to see some copycats in the market now. And you have to admit, there's something really exciting about getting an OCT machine for $10,000 when most of them cost well north of $50,000. Door Lab's research system may cost $80,000. And I'm happy to say a lot of these companies have sort of ceded that research area to us. There's no one else that's even close to us on price. And we're able to have these out there at a very competitive price point.
Yeah, that's awesome. And it's my understanding that are they more portable now?
They are. So, OCT machines typically would take up a whole desk. Maybe another unit here, and you need a whole PC. Ours is about the size of a shoebox. You pick it up and carry it with your arm. There's a built-in computer, so you don't need a laptop or anything with it. And then you can use a screen, or you can use a Bluetooth phone or tablet to control it. So the whole thing weighs, I think, in the order of let's say less than 10 pounds right now.
Okay. Do you see this device having the potential to be used in other parts of the body?
We have done many experiments in other parts of the body. So, OCT has been used in the GI tract. It's really exciting to develop a fiber optic probe and be able to probe, the lumen. Part of the problem is that OCT is a microscopic imaging technology, so you're imaging a really small part. But for example, the esophagus can be, 100 square centimeters that you have to examine. And you can't do that, millimeter by millimeter. So you have to come up with some way to look at those broader areas. We've also done some work looking at OCT of skin. So we've looked at burn depth, skin cancer. We've done dental, where you look at teeth. We've done cervical cancer imaging. We just finished a project in colon polyps. I think these are all viable technologies, but the question is, can you make it to the point where it can be a commercial technology, right?
As we've done in class before, we wanted to go through the implications of OCT technology, first beginning with the kind of radiation, the cost, and the speed of scans. As we discussed, OCT uses infrared or near-infrared electromagnetic radiation. In terms of cost, one scan is relatively cheap, anywhere from about $40 to $60. However, it is more expensive to install a machine, anywhere from about $50,000 to $120,000. Each scan only lasts about 10 minutes, so it is a pretty quick imaging modality. The resolution of OCT is limited by two things: the finite pixel size of the line detector and the diameter of the incident beam. And contrast, similarly, is limited by the length of time delay between the reference and sample beams. Some strengths of OCT technology include its speed, again, very fast scan, the fact that it's non-ionizing radiation, so it's pretty safe for users, and the resolution is very high, and it can be as high as 1 micrometer. However, the main weakness associated with OCT is that it is currently pretty expensive and hard to maintain for a simple scan that is very preventative. Finally, some system components of OCT include the optical probe, the low coherence light, the mirror, and the interferometric detector.